We said that about blackout. The blackout maybe occur or happens in power systems, which is very important issue or subject in power systems, or shutdowning uh, each generator by under frequency relay, and the whole power systems is blackout, and restoring the power systems may be very complex to restore after blackout. The recent blackout was about Australia. In if you search uh, Australia blackout, and this was a recent blackout in Australia, and losing power systems or electricity in Australia. Another word for define the blackout is outage. And after that, we introduce two control systems regarding the synchronous generator. The first control system is about governor. We sensing the frequency of power systems compared with the reference, and we defined how the steam valve must be open or closer than before. And after that, the speed of the steam turbine is changed, and this changing of speed may compensate the power system frequency. Another control system is called AVR, automatic voltage regulation. We sensing the terminal voltage and comparing with the voltage reference, and this voltage reference, and comparing with the real parameter of voltage, terminal voltage, make the excitation systems and changing the flux of flux to stator, and making the ideal voltage of terminal in generator. After that, we depicted mechanical and pneumatical systems to compensate the frequency and the control of steam valve, and but the new one is electronic board. After that, we introduce a controls block systems for modeling generator, modeling turbine, and we introduce also two input to this control systems as delta PC. Delta PC means the manually changing in power. For example, if I want to generate more power manually, it's affected on delta PC. Another input is delta PD. Delta PD means the any changing in demand as input, and any increasing or decreasing demand should be applied here. And this closed loop depicted that the relation between the changing active power as delta PC or delta PD in frequency. All this control system is defined in frequency domain and in Laplace mathematical mode, and the transfer function is defined delta Fs when delta PC is 0. This is the transfer function as delta PD is a step. And this formula in red line table um, tell us about how the frequency behave in changing the delta PD as a step. And this is response of a step input in delta PD. And we define that if what you want to make inverse Laplace to get time domain of delta f, this is minus delta PD on B plus reverse of R. B plus reverse of R is defined as droop, but in many cases the B is 0 and the droop is minus R. And the final value of frequency with changing the PD and supposing that delta PC is 0, this is the final value, and this is it is minus copy delta PD on 1 plus Kp on R. Another important issue is about changing delta PC as a manual, changing in active power manually in a step as a step response. And this is the transfer function to define delta Fs when delta PD is 0, and this is a final value. After that, we introduce the how we can compensate when your percent of load is decreased from 100 to 60%, and you have to decrease this point. This point is no load position, and the no load position is affected by turbine in speed, and you can change the no load position for occurring or happening the any percent of loads in 100% of frequency. So we now we have two main transfer functions. The first one is the effect of delta PC on delta Fs, and the effect of delta PD on delta Fs. In many cases, the amount of Tg as we defined for generator, Tt as defined for turbine, Tp is defined for power systems. The Tp is very much than T and Tg, and in many cases we can ignore Tt and Tg regarding in or opposite to T of P about power systems. We are here examples. For example, delta PD is 0.01 as changing in active power. This means that the load changed 0.01 per unit as input of load frequency control system. Delta PDS is 1.01 over S in Laplace. The time constant, the TP is time constant of power system. Tg is time constant of generator. Tt is time constant of turbine. Kp means B inverse is 100. The time constant of power system is 20 seconds. Droop is 3. And so if you want to calculate the final value of delta F in the final value of delta F in changing delta PD. It's like here. For example, for this example, delta P could be here, and R is 3, Kp is 100. The tau is defined as Tp in R over R plus Kp. R is 3, Kp is 100, Tp is 20. And after that, after calculating these parameters, the delta F is here. In steady state mode, state, in a steady state, we have to turn the time to infinity, and these parameters goes to 0, and the delta f in steady state is minus 0.0291 Hertz. This means that if the load increase 0.01 per unit, the frequency decrease minus hertz. For example, if you work in 50 hertz, after increasing PD as per unit, your final frequency nu, this is a frequency in old mode, the nu is 50 hertz minus hertz. And this graph shows that this is delta F. The delta F is 0, and after increasing the demand as this amount, the frequency increases as 0.291 Hertz. Okay, so this is an example to shows that the increasing in delta P, increasing the delta P decrease the frequency. Okay, maybe you ask me about how the delta ft is defined like this. We have to say that delta fs, we have two equation about delta fs. When the delta pd is 0, when the delta pc is 0, and if you replace this parameter with the real amount of the examples, you have to inverse Laplace. You have to calculate the Laplace inverse. The delta f in time domain is Laplace inverse of delta fs, and we calculate the inverse of Laplace of delta fs and find delta ft like this. Another important issue is about is about, okay, when you find out the increasing the delta PD may be cause or effect on delta F, and increasing delta PD in decrease delta F, or increasing delta PD may decreasing delta PD may increase delta F, and this increasing or decreasing of frequency is not ideal, and you have to turn the frequency to the standard. For example, in this case, we lose 0291 Hertz, and we have to compensate this frequency with a parameter. Which parameter? The parameter is delta PC. The delta PC can compensate increasing in decreasing of frequency and we have to add a supplementary loop here. This is an old version of load frequency control. The frequency is sensed here, changed with droop to power here, and the power compared with delta PC, and delta PC through pass through this block diagram about generator, turbine, and after that delta PD can be added and compared, and after that applied to power system model. So this green line of controller said that the delta PD increasing, that makes delta F decrease, and for compensating this frequency decreasing, you have to increase the delta PC to compensate the delta F, and after that the delta F would be 0. This means that no changing in frequency happens. The amount of decreasing the frequency can be compensated with manually increasing active power with opening steam valve, steam valve, more. So we sensing sensing the final frequency here. After that, we make an integrate controller based controller to define how the delta PC must be determined to compensate the decreasing of frequency. So the the frequency and the transfer function, our transfer function, transfer the transfer function could be modified as here. As here. And so the final value of delta Fs, the final value of delta Fs is 0. In mathematics, in mathematics and Laplace, we have a theorem of final destination. The final destination said that if Fs is Laplace of Ft, if you want to calculate the final value of t, final value of f, it is a limit of s f s when s turns to 0 or goes to 0. This is called final destination theorem. And for this transfer function, if you want to calculate the final value of ft when t turns to infinite, it is a limit of s fs when s turns to 0, goes to 0. Limit of s multiple to kp delta pd, we write like this: on 1 plus stp. You have to memorize these transfer functions in this chapter. Memorize. Lies KIS multiple to KP STG 1 plus STT delta P ds. This is clear with another S. This could be 0, that could be 0, 0, and this is limit of Kp, excuse me, delta Pd is not correct here, Kb delta Pd plus 1 plus minus reverse of R plus Ki over S in Kp. If S turns to 0, this is limit of Kp delta Pd on infinite, and this is 0. This means that if you add the yellow highlight as a supplementary control system for compensating the decreasing of frequency, the changing of frequency affected by delta Pd could be compensated, and delta F in time domain, delta F in time domain goes to 0. And if 50 Hertz for increasing delta Pd, the frequency decrease, and after the controller, after this controller, the frequency return to the main value of 50 Hertz, and this decreasing is compensate. Okay, the chapter 6 is finished, and after that I want to work about the per unit. I want to talk about the per unit systems. Per unit system is fundamental knowledge about power systems or power system operation. I'm very eager to talk about per unit system and review your skill to find per unit. We before talk about the per unit, and now we want to review the per unit systems. When we want to use per unit, we want to simplify our power systems, which consist of many transformers. The transformer, when you use transformer in power system, for example in generator, produced 20 kilovolts, and after that we use a transformer and increasing the transformer and step up the voltage to 400 kilovolts, or decreasing the loss after transmission line. We have to decrease the voltage to 400 kilovolts to 230 kilovolts, after that 132 kilovolts, and after that 63 kilovolts, after that 20 kilovolts, and after that 0.4 kilovolts or 400 volts in consumption. There are many transformer, high voltage transformer, and the transformer makes our power system more complex for finding voltage and current in each section. For example, if you want to calculate the current here, you have to get back from the primary side, and this primary side is secondary side of this transformer, and you can get back and get back and get back, and finding I of generator, and comes to forward to finding this current. For remember, this transformer has the number of winding, the number of turn of the primary winding as N1 and N2 is secondary one, and the transfer ratio as defined as A, N1 over N2, and the voltage in primary, voltage in secondary, V1 over V2, and I2 over I1. I2, I1. And you have to calculate this current in this section with going a step back and finding IG, and a step forward and go to forward to finding I. This makes the power system and calculation very hard, and the per unit could be helped. The per unit says that you can change the transformer to an impedance in space, in mathematical space, in real one, real environment. It is mathematically environment. You can model transformer to an impedance. This space is called per unit. Actually, you use the per unit in real world. For example, if you want to go from Baghdad to Frankfurt of Germany. You have to change your currency to euro, and if you want to travel by foot here, and you first go to the Turkey, and change your money to lira, Turkey lira, and after that to Bulgaria, and changed your money to Bulgaria, and changed your money to the currency of Romania, after that the currency of Hungary, after that you have to change to currency of Austria. The Austria is in European Union, and the European Union use euro, and this is not necessary to change your money to Germany currency. The Austria and Germany is the same. The changing your currency to the destination current country, that will be the model with transformer. The transformer transfer your currency here to currency to Turkey, and in the real world you uh, don't do that, because if you want to travel by foot to travel from Iraq to Germany, you change all of your money to dollar and euro, or euro, and the euro and dollar means the common unit wealth. The euro and dollar is common unit wealth. It means that your wealth. It means that your currency, dollar or euro, is in all of country is valuable. In many years ago, before the currency is invented, the Commonwealth was gold. The gold and valuable metals was very valuable common wealth to travel. For example, if you want to go and to travel in the world, your your financial effort could be transferred to gold or silver to transfer. But in new world, the currency of euro and dollar, especially in dollar, you can change your money to dollar and travel all the world. The dollar is valuable. So the dollar or euro is a common unit wealth. In power system, we tell that per unit. Per unit. For changing your money to a dollar, you have to calculate your money in each currency to the base value of dollar. For example, in uh, Iraqi dinar, 700 Iraqi dinar is equal to $1. For example, I don't know the exact value. Iraqi dinar is $1. This is the base value to changing your money for transfer your money to dollar. And after change your money to dollar, you can delete all transformer here. We delete transformer, and it is no need to change your currency to the uh, country you go. For example, your currency in dollar is valuable in Turkey. This currency is in dollar is valuable in Bulgaria. Currency in dollar is valuable for Romania, and your currency in dollar is valuable in Hungary, and your currency in dollar in Hungary is valuable, and it has the same value in Austria, and your currency is in dollar or euro is valuable in Germany. With changing your money in dollar or euro, your power, your currency power is remain for traveling each country. For example, $1 million is more valuable in Iraq, $1 million is more valuable in Turkey, in Bulgaria, Romania, Hungary, Austria, Germany. In very years ago, the gold has this role. Okay, so when you want to change the transformer to in per unit system, the per unit system is mathematically, you have to divide your power system in many zones. Which zone? You draw a border in the middle of transformer. And the zone is established like this. This is the first zone. The middle of transformer to another transformer is zone 2. This is zone 3, zone 4, zone 5, the zone of 6, and the zone of 7. In each zone, you have to determine 4 parameters as four parameter as base value. The first one is base value of power. It is called SB for Zone 4. V based for current base of Zone 4. Impedance based for Zone 4. SB5, VB5, IB5, ZB5. The S in each zone is equal to each other. The voltage is defined. The current is dividing the base of power on voltage. The Z is dividing voltage on current, or voltage square on power in each zone. I give you an example to clear the subject more. Suppose that we have a transformer like this in power systems, and we have an impedance is 3 ohm. The primary side of transformer is 500 volt to 1000 volts. S base is 10 kilovolt ampere. We divide the middle of transformer and finding zone number 1 and zone number 2. The base of power in zone 1 is equal to the base of power in zone 2, 10 kilovolt ampere. The voltage of base 1 is 500 volts, and the base volt of zone 2 is 1000 volts. The current base current in zone 1 can be calculated 10 kilovolt ampere over 500 volts. (200 amperes). Uh, 200 no, 20. IP2 is 10 kilovolt ampere over kilovolt, means 10 ampere. The base impedance of one is calculated like 500 volts over 20 amperes, means 25 ohm, or 500 volts square over 10 kilovolt ampere. ZB2 is 1000 volts over 10 ampere, means 100 ohm, or 1000 volt square over 10 kilovolt ampere. After finding these four parameters, you can change your these power systems to per unit 1. This is A, this is B, this is A, this is B. This called that impedance of transformer in per unit. This is a Z in per unit. Z is 3 ohms. This Z is located in secondary side of transformer. The secondary side of transformer has the base of 100 ohm as base. So we can calculate 3 ohm over 100 ohm. That means 0.3 per unit. And after calculating these four parameters, you can ignore or delete transformer and change the real world of our system to mathematically space or per unit space. This is a brief reviewing of per unit. We taught you before about the per unit. We discussed before. I give you some more examples in next sessions about the per unit. If you have any questions, I would be happy to write to me your questions in WhatsApp, and I will answer you your question. In our class, we discussed over yes the load frequency is finished and only Newton-Raphson is remained. Newton-Raphson is remained. In Newton-Raphson we try to calculate the power flow by Newton-Raphson method. Newton-Raphson is more complex, but we have to review this method notes and maybe solving an example about the Newton-Raphson. And for Newton-Raphson we also do exercise with type 1, the network type 1, and the network type 2 as a PV bus here. And the next sessions we try to learning about Newton-Raphson. Do you have any question? If you have any question, please write it to me in WhatsApp. And thank you for coming in my class. Have a good time. Thank you very much. Goodbye.